Hi everyone, in this video we're going to talk about section 8.4, which is on trigonometric substitutions. So this is when we're dealing with integrals that have certain forms in our integrand, and we're going to use trig functions to replace part of that, and specifically our variable. So let me read this bullet point. Replace a variable of integration with a trig function. So like where there's an x, it's going to get replaced with a trig function. Most common substitutions are the following, and I just labeled them 1, 2, and 3 so we can reference them easily. X is going to get replaced with a times tangent theta. And when we do this, it's when we have the form square root a squared plus x squared in our integrand. Number 2, most common substitution, x is a sine theta. And we'll use this one when we have square root a squared minus x squared. And then last, the most common one is x equals a secant theta when square root x squared minus a squared is in our integrand. So a is going to be a number in our problems. We'll recognize and figure out what a is. But let me show you where this comes from, so you are not thinking like this is super random why we came up with these trig substitutions. So let's just do them one at a time. We'll start with number 1. If you think of a right triangle, okay. And with this right triangle, you can say, well, here's my angle theta. We'll call it this angle in this corner here. And if I say that, think about tangent really quick. If I say that tangent theta, tangent my angle, if you solve for it based on this substitution here, look what we have. If you solve this for tangent theta, you're going to divide by a. So x over a. And we know tangent is opposite side over adjacent side. And then if you use your Pythagorean theorem, think about what this side would be. So we know a squared plus x squared is the hypotenuse squared. And if you solve for that hypotenuse, you'd square root this. So this side length is a squared plus x squared. And so that's why when you see this in your integrand, you're going to use tangent theta times a to replace x. And we'll work through all the steps so you'll see what's going to happen nicely when we do this. So let's continue. Let's figure out why we're going to use a sine theta for x with this type of integrand. So sine theta, if you solve it from here, just divide by a, is x over a. And we know sine is opposite over hypotenuse. So if you use your Pythagorean theorem, we know that this leg squared plus this leg squared is the hypotenuse squared. And so if you solve for this missing leg, you would subtract x squared and square root it. So you'd have a squared minus x squared and then square root that. And so that's why this is going to be useful when we have that type of setup in our integrand. And for the last one here, so secant theta, same process we've been looking at. If you solve for it, we know that it's x over a. So all of these, notice, our trig function always equaled x over a if you just divide out a. And so secant, if this helps you, rewrite it in terms of cosine. Secant is the reciprocal of cosine, so that means cosine theta is a over x, if that helps you. So cosine of theta we know is adjacent over hypotenuse. And so again with our Pythagorean theorem, a squared plus this missing leg squared equals the hypotenuse squared. So if you solve for this missing leg, you'd have x squared minus a squared inside the square root. Alright, and then so notice that's what we're saying is the type of integrand you'll see. A times secant theta would be a good substitution. Alright, so I'm going to remind you also something about inverse trig functions, and then we'll get into our first example. Okay, so let's remember something we know about finding this angle theta if we have a trig function of it. So just a reminder of our common substitutions we're going to end up using. Let's focus on the first one. So tangent theta is x over a. So if you want to solve for theta, you would have to use tangent inverse. And you would get that theta is tangent inverse of x over a. Alright, so why I'm mentioning this is because when we use this substitution, some of the time we're going to need to use inverse trig functions to find our actual theta value. And then from trig, when you first learned about inverse trig functions, there was a restriction on the original trig functions domains. And so that turns into a restriction for the range of these inverse trig functions. So here's what I'm talking about. This is only valid for theta values between negative pi over 2 and pi over 2 for tangent inverse. So it's a definition for tangent inverse that the domain was originally restricted on tangent, so that when we use tangent inverse, the range is between these two angle measures. Okay, so just going all the way back to trig really quick, if you think of your unit circle, this is quadrants 4 and 1. So from negative pi over 2 is quadrant 4 to positive pi over 2 is quadrant 1. So it's angles in this region. And then we'll just do very much the same thing, give you the restriction values for the other two thetas if you're using sine and secant. So in this case, theta would be sine inverse of x over a. And the only difference with the restriction for this one on theta is that you can actually equal the pi over 2's. So theta has to be between negative pi over 2 and positive pi over 2, but you can equal them. It wouldn't be undefined like it would for tangent inverse. Theta, last one, is secant inverse x over a. This one's a little funny because we have to do like a jump. So theta is between 0 and pi over 2, but then also theta can like jump over pi over 2 and then go until pi. Okay, and then this is true whenever x over a is greater than 1 or more, and then theta would live in this region if x over a was ever less than or equal to negative 1. So let me just show you with the unit circle really quick. So we're talking about angles or theta measures from 0 to pi, so 0 until pi, but we're not including pi over 2 because secant would be undefined right there. And so what we're saying basically is that you're going to get a theta between 0 and pi over 2 in quadrant 1 over here anytime your x over a is more than 1 or more. And then you're going to get theta to be in quadrant 2 over here anytime x over a is actually negative 1. So this, you don't have to worry too much about this, but I did want to remind you what you knew about inverse trig functions before we get into our first example. Jumping into example 1, we want to integrate 1 over square root 4 plus x squared dx. And I did leave what we had figured out or talked about initially about our substitutions up here. So I'm going to break this into steps for us. So step 1 is going to be to basically identify which function you want to use. And I have the reference here when you're going to use this. You don't necessarily have to memorize when, like what the format of the integrand should look like, but it does help. But you can always draw your triangle. So hopefully you can see which one we're working with. Right now, let's see if I draw my right triangle. I have something squared plus something squared. So it's got to be the hypotenuse. And so let's say I'm basically saying if I didn't know this, if I didn't know when to use these. So if I have square root 4 plus x squared, and so I'm going to say that this is x and this is 2, because 2 squared plus x squared would be this quantity squared. And so then if this is my angle theta, I know that tangent is going to give me x over a. So tangent theta is x over 2. And so if I want to solve for x, I know that x, if I times both sides by 2 here, x is 2 tangent theta. Alright, so I'm showing you how to pick the right trig function to substitute, but from what we already listed, you can kind of just look at number 1 and see that it fits this integrand, it matches something squared plus x squared. And so right away you can identify that a is 2, and you would just say x is 2 tangent theta. So I just kind of broke it down for you there. Alright, so that's what I would call step 1. And so step 2, I'll just write it here, is to find dx, because you're going to substitute that also. So the derivative of x, and this is technically with respect to theta, so I'm going to move the d theta over, but I'll put it here just to show you. The derivative of x with respect to theta is 2 derivative of tangent theta secant squared theta. And then what we usually do is we skip this step where d theta is here and we just move it here. So times both sides by d theta, and then that's dx. Okay. And so step 3 is going to be to substitute these values and to simplify. All right. So jumping into our integrand, we have the integral of 1 over square root 4 plus, we have let x be 2 tangent theta. Now be careful, put parentheses because you are squaring this quantity because this was x squared. Okay, and then dx is all of this. So dx is 2 secant squared theta d theta. Okay, so why is this a thing? Why do we do this trig substitution? This looks pretty messy, but it actually is very good. Let's work this out. So we're on the simplifying part, and here's why this is a good method to use. I'm just going to focus on this square root for just a minute so you see where we're going. This square root, we have 4 plus, square the 2 and square the tangent. 4 tangent squared theta. Let's factor out a 4. Okay, I'm still just working on the square root. If I factor out 4, I have 1 plus tangent squared theta. Okay, and now we remember, hopefully, we talked about this in the last section. One of your identities looks like this. So if you recall, this is secant squared theta. Okay, and so if we know this is going to turn out really nice because basically we're going to get rid of the square root with this process. And so this becomes square root 4 secant squared theta. And then square root this. Square root of 4 is 2. Square root of secant squared is secant. So this is all 2 secant theta. And that was our denominator. Okay, so let's make this look a little better. I'll just kind of move over into this corner real quick. We have the integral of, I'm going to move over this 2 secant squared theta just on top of my fraction here. So 2 secant squared theta. I'll leave this d theta in the back. That's just moved up on top. This whole square root down here became 2 secant theta. And this is so nice. Hopefully you're seeing the simplification as we keep going. The 2's divide out. This is the integral of secant theta because one of the secants divides out as well. Okay, and then we know what this equals. Alright, so I'm just going to squeeze it in here really quick. This is ln, and if you don't know this one, it is on your table 8.1 from section 8.1. So this is ln secant theta plus tangent theta. Now, I can't box this in because my problem had x's in it at the beginning. Way back at the beginning we were dealing with x, but we substituted, notice we have the thetas in here. So we need to rewrite this answer. So I'll just kind of circle this answer for now. Circle this, because we're going to have to modify this for what we substituted for x. Okay, so let me just clean this up a little bit. So continuing, this is the answer we had just came up with, but we need to resubstitute. So I'm going to call that step 4, because we had x's to begin with, and now we have thetas, so we need to go back. So resubstitute. Okay. Now you can do this 2 ways. I was mentioning the inverse trig functions, but you can also, some of the time, you don't have to use them. So here's what I'm talking about. We had this here just a moment ago. We had that tangent theta was x over 2. So we know if we want to just solve straight for theta, theta is tangent inverse of x over 2. And so everywhere there's a theta, I can go ahead and plug that in. But then I'm going to get secant of tangent inverse, tangent of tangent inverse, which that one's actually nice. But I'm going to avoid it on this one. I will show you an example where we can't avoid this. I'm going to just go straight back to this triangle that we drew. So here's what I would use in this problem. From my triangle, my right triangle where I came up with this relationship, I can figure out secant theta and tangent of theta. Theta is this angle, and I know secant and tangent are just ratios of sides of this triangle. So from this triangle right here, we know that secant of this angle, so let me just remind you in case you forgot, hypotenuse over adjacent is the definition of the secant of theta. So in that case, it's square root 4 plus x squared over 2. Very much similar. From this triangle, we know that tangent of theta, and tangent for our triangle is opposite over adjacent, so x over 2. And so from here, our answer, let's just draw some more arrows here. We have that our integral of 1 over square root 4 plus x squared is ln, absolute value. Secant of theta was square root 4 plus x squared over 2 plus tangent of theta, which is x over 2, and then just put on our plus c. And this would be our final answer. And so this is how we use our trig substitution. Okay, so I want to tell you something about this answer, just to make a mention of this, because this is an interesting function that we have going on here. So let me just erase what we were working on. This is more of a side note, and it just has to do with the format of the answer. If we generalize this, I'm going to use a instead of 2. So if we have ln of square root a squared plus x squared over a plus x over a, this is actually equal to a different function. This is hyperbolic sine inverse of x over a. So when you see this, you can call it sinh, that's one of the ways it's pronounced, or you could say hyperbolic sine, but it's hyperbolic sine inverse or sinh inverse. And so it's just interesting. This is an actual other function. And so just another note for you. So the hyperbolic sine function is, you can pronounce it sinh or hyperbolic sine. It's equal to e to the x minus e to the negative x all over 2. So we won't go into much detail about this. I did just want to give this to you because you might come across this in the future. But this is a function that sometimes comes up in applications, hyperbolic sine function. And this happens to be the inverse of it when the argument is, sorry, let me throw an x in here. This is for x. When the argument is x over a, this is the inverse of this function, this answer we had just came up with. So just an interesting side note.